Okay, so Kenya came in this morning, and a lot of people are asking about this. She came in this morning. We worked the problem on the backboard. That's why there's no quotes, but um, it made me realize that maybe some of y'all um, are struggling as well. And so I'll just look at it a little bit differently, kind of breaking it down. And if you ever, and Ellery came in last week, I gave her more problems to work. I'm always here, right? I'm here every morning when the door's open. You can ask me during advisory, sea lunch, conference period 7th. Um, if something's ever troubling you. So if this is a graph of F prime, and we're looking to answer questions about F double prime, which I redid over here, then again, you have to calibrate your brain, right? So now you would say, we want to sketch the slopes of this graph. I'm sorry, this is supposed to be sketch F double prime. We want to sketch the slopes of this graph on the same coordinate grid. So the X's have to line up. So this is then where we say, okay, what do we know about the slopes of F prime? Or whatever the name is, right? This could be the graph of the 5th derivative, and we're sketching the 6th derivative, right? We know the slopes are going to be 0 where we have local max and mins, okay? If it's continuous, it could be DNE, but this one's defined everywhere. So the first thing you would do is put down those points. Those are zeros, okay? So wherever we have a horizontal tangent, and there's 3 of them, you put down your x-intercepts. And then you just analyze in between there. You want to see, is my graph increasing or decreasing? Okay, if my graph is increasing, I'm going to sketch positive y values. If my graph is decreasing, I'm going to sketch negative y values. And then you want to see how it's increasing, how it's decreasing. Is it getting bigger or smaller? So this is where you can assign arbitrary values. Okay, so this could be like a slope of 10. This could be like a slope of 1. This could be like a slope of a half, right? What's happening to 10, 5, a half? They're getting smaller, right? So my slopes are positive, but the slopes are decreasing. So I'm just going to draw a line coming down. There should be an open circle at A. It's coming down, okay? Now, the way that if this is a polynomial, polynomials are curved nicely. So it's going to come in concave up, not concave down. All right, and then you look on the next interval between those 2 x-intercepts you drew. The function is decreasing, so my y values that are going to be the slopes are going to be negative below the x-axis. So again, you can put arbitrary values there. This is going to be like a negative a half, a negative 5, and then back to a negative a half and 0. So what's happening? The slopes are becoming more negative. I put this little dot here because that's going to be like the implied inflection value. I don't know exactly where the value is, but that's where it reaches its lowest. So you just kind of continue your curve. So somewhere right there, that's going to be the lowest, and then the slopes start increasing again, okay? Again, 0, negative a half, negative 1, maybe negative 3, and then back to negative 1, negative a half, 0. So my slopes decrease to a low point, come back up. And then we keep on going, right? Now on the next interval between the zeros, we have positive slopes, positive a half, positive 1, maybe positive 3 at the inflection value, and then positive 1, positive 0. So right there where 3 is, it reaches a high point. Now, do I know how high it goes? No. I'll just kind of come back down nice and smoothly. And again, you could have made that lower. And then to the right again, we have negative slopes. So it's going to be below the x-axis. Put arbitrary values, negative a half, negative 1, negative 10, negative 100. So from there, it's decreasing. And you can make it curved. And then at B, we put an open circle because derivatives will never exist. Now, though that graph has to have those x-intercepts, but the severity of how steep or how high or low you go, it's up to you, right? I could have started here. I could have made it a little bit more shallow. Look something like that. Come back down, boom. It's entirely up to you. It's just qualitative, but the x-intercepts have to be there, all right? And then we would label it F double prime. So far, so good? That's good. Yeah, now I went with this one. It was easy. There's no discontinuities. There's no cusps. If there was a cusp for something, you would just put an open circle in the interior. If this graph had a vertical tangent, then that's where you would draw your y values going to infinity or negative infinity. That would be a vertical asymptote. Okay. Now going backwards, I think, is the fun one. Going backwards is where you have to really analyze both the y values of f prime and the slopes of f prime so that you can sketch your graph according to that broken circle that we talked about at the beginning of that section. If you know both signs of both the first and second derivative on any interval, it's going to take one of those shapes. So the graph of f prime, when you're asking questions about f, I've said it in class, it's better than a number line chart. But let's go ahead and look at y. You've got two values where the derivative is 0, okay? And let me just mark this. I'll just mark this as 4 just for convenience. So if we were to be finding critical values, we would take the derivative of f, set it equal to 0, see where it's undefined. This graph is defined everywhere. And where is this graph equal to 0? Well, it's equal to 0 at 0 and 4. We would then create a number line chart, x and f prime, and we would put 0 on the number line, and we would put 4 on the number line, yeah? And then we would pick values like -1, 1, and 5, and we would plug them in to the equation to see if they're positive or negative. Well, you could see that, oh, we have another critical value. Sorry, my bad. Yeah, y'all are looking at me like, what the heck? There's another x-intercept over here. I just don't have it marked. Let's call this one -3. So here's -3. Okay. And then I would pick values like -4, -1, and 1 still works. We have whether the y values are positive or negative, but we also have kind of where they're positive or the relative values. So what would the derivative f prime be to the left of -3? Well, our graph is below the x-axis, so we know it's going to be negative. It would be negative immediately to the left all the way to a. What do we know about the derivative between -3 and 0? Well, my f prime values are above the x-axis, so we know it's positive. What about the derivative values between 0 and 4? Again, the graph is below, so we know it would be a negative. And then to the right of 4, it's below, so it's going to be negative again. When we have the number line chart, then maybe you're used to saying, oh, when f prime changes from negative to positive at a critical value, there's a local min there. Whenever f prime changes from positive to negative at a critical value, we have a local max there. And when there's no sign change, negative on both sides, it looks like that. That's kind of already part of the sketch of f, right? We're just kind of inferring the concavity. Now, the other thing that we would do is look for inflection values. So that's where we would make a graph, a number line chart of x and f double prime values. We would look to see where the second derivative is undefined. So for here, that's going to be at 0 and 3. Okay. That's the only two places, right? If you look at the graph of f, concave down like frown, concave up, concave down. Then we would pick values like -1, 1, and 4. And we would plug them into the factored version of f double prime. Well, we kind of know what the curvature is, right? It's concave down like a frown, so that would be negative. It's concave up like a cup on the next interval, and then back to concave down like a frown. When you combine these two, right, then you get a clear picture of what the graph is doing. But we have that. Oh, yes, food donations, bring it in. Thank you, thank you. Okay, so if we were doing the analysis for inflection values, we have our pivotal values at 0 and 3. Both of them change signs there, so they're both actually inflection values. Okay, so when we put it all together, what we're doing is we're analyzing then both what the y values of f prime are doing, and we're analyzing what the slope values of f prime are doing. Okay, because the y values of f prime, of course, give us f prime values, and the slope values of f prime give us the inflection values. Okay, and then we just put it all together. So let's go ahead and do that. I'll move this down. And when I talked about shifting, I'll explain again what that means. We're going to look now on each interval, and wherever our y values change sign or the slope values change sign, we're going to reanalyze, okay? So on the first interval from a to -3, f prime is negative, f prime is negative, so I know my function is decreasing. It could be decreasing at a constant rate, increasing rate, or decreasing rate, okay? How do I know which one? Well, I look at the slopes, okay? On the interval from 0 to -3, the slopes of f prime are positive. When the slopes of f prime are positive, the second derivative is positive, and my graph is concave up. So I know it's going to look like that, okay? So what I like to do in my head is just in this order, I look at the y values, and then I look at the slope values. And this is on the graph of f prime. Okay, so in this case, my y values are negative and my slope values are positive. When I make the shift, it's me basically translating it, to what f is doing. If my y values are negative, it's decreasing. And if my slope values are positive, it's CC up. So that's where I make the shift, okay? Does everyone understand what I'm doing? Negative y values, positive slopes. So I just tell myself negative, positive, negative, positive. Oh, that's decreasing concave up. So now we'll come in and draw a piece that's decreasing concave up. Now it did tell us to start at 0, -2. No big deal. That is going to be, I'll just say that that's right here. Well, I don't use purple. Let's use, I use green. So 0, -2. I have to hit that mark. I've already started, so let me just go ahead and start anywhere. So it's going to be decreasing concave up. Decreasing concave up is going to look like this on that little interval. I'll move it and connect it later. Okay, boom. Now I do hit horizontal there. Now on the interval from -3 to 2, I have positive y values, positive slope. Positive y values, positive slope. Now shift it. That means increasing concave up. Increasing concave up till I get to right there at -2. And then from -2 to 0, I have positive y values, negative slopes. Positive y values, negative slopes. That's positive, negative. That's increasing concave down. And that's where I go to a horizontal tangent line. So notice now I need to make sure I hit my mark. So I'm just going to move that down. Boom. And then we'll call that -2. If I had started graphing it way up above, I would need to move it down more. All right, now on the interval from 0 to 2, what do I have? I have negative y values and negative slopes. Negative y values, negative slopes. That's negative, negative. That's decreasing concave down. Boom. From 2 to 4, 2 to 4, I have negative y values, positive slopes. Negative y values, positive slopes. Negative, positive means decreasing concave up. Decreasing concave up to a horizontal tangent line. And then finally from 4 to B, I have negative y values, negative slopes. Negative y values, negative slopes. So that's decreasing concave down. Boom. And there you go. That would be the graph. If I've given you a different value instead of 0, -2, like 0, +2, the only difference is that graph would be elevated. All right. What's important to match up are the following, right? Your x values, your x-intercepts have to coincide with the local max and mins. Okay. And then the high points have to coincide with your inflection values. The local extrema of f prime, remember, are your inflection values of f. So again, notice f prime has a local max at -2, and that's where f changes from concave up to concave down. F prime has a local minimum at 2, and that's where my graph changes from concave down to concave up. And then it has another local maximum at 4. That's where my graph changes from concave up to concave down. All right. So practice that, put it all together. I just did a real quick Google search when Ellery was in, and I just did sketching F prime and F double prime from F. And then I looked up, I did a search type for PDF files just so you can download them easier. But there's lots of stuff out there, okay? And it's just how much practice do you need? If you're not comfortable picking your own problems, come see me. I'll find some more, okay? I've got textbooks too that I can send you home with overnight or for a week or so if you need to borrow them. Or you could, anyway, if you just say sketching graphs of F prime, F double prime, it's all kind of one big can of worms. But anyway, that's that. All right. The graph of F prime is better than a number line chart. And of course, y'all know how to justify that, right? About talking about a sign change, pivotal values, inflection points. All right. Any questions on that? Maybe we'll practice tomorrow with a quicker warm up where I give you a discontinuity or something like that. Or a quiz. Yeah, a quiz. Yeah, okay, good. All right. So let's return to where we were last time. We are actually on example 9. So this is just a strange coincidence that we're on example 9. And it is aluminum can appreciation day. I kid you not. Yeah. On this day in 1935, the first aluminum can for a beverage was manufactured and released to the public. It wasn't soda though. It was beer. It was the Kruger Cream Ale, sold by the American Kruger Brewing Company. And the original cans, there were 12 fluid ounces, and it came in a cylinder. They also sold a 32-ounce version that had kind of a peak top, but a lot went into the design of the soda can, right? Soda cans became, they were in glass before that, and glass was heavier, more expensive, broke easier. They didn't stack as well. These things are genius. Now, this is the can that I'm going to pass around. This is, of course, the closest I can come to a beer can. It's root beer. And it's really close to a true cylinder. Of course, it has a little bit of edging on the top and bottom, but the original can had a solder down the side. It was a steel can actually, and they would use a steel solder. So sometimes the beverage inside, you would taste a little bit of that metallic taste, Yeah, isn't it so good? And then the tops, this is an original pull tab that is not pulled, so don't pull it. But you could see that when you pull it back, you would peel it off, and then you'd just be left with this sharp metal thingy in your hand. And a lot of times they didn't end up in the trash can. They ended up on the ground or on your foot, right? If you walk across it, you get cut. And the story I heard was supposedly in 1984, Governor Mark White of Texas was walking on the beach, and he stepped on one of these pull tabs and sliced his foot open. And he started legislation to get those things to be designed differently. And today, of course, you know that when you open it up, it stays on the can. So this can right here, again, is kind of like, well, it went through several designs before this, but this is kind of like the prototype to what we see today, because the soda cans of today are highly engineered, marvelous feats of engineering. Yeah. Oh, for lack of a term. So I'm going to pass this around. You can take a look at it. Don't pull the tab. Don't pull the tab. Don't pull the tab. Okay. Just look at it. It's drained. There's no root beer in here. If you want to look at it, you can. And then you can compare it when you get home to a real can. Okay. So what considerations went into designing the first can? Well, somehow they decided that 12 fluid ounces was going to be what they wanted to put in there. Right? Like they had already done some studies that said the average person could drink 12 fluid ounces one sitting. And you're telling me you did not plan that? I did not. It just happened on soda can day.
You're being serious. You actually didn't plan it.
No, I didn't. Okay. So 12 fluid ounces is 21.6562 cubic inches. So once it was that, they turned it over to the engineers and said, we're going to build a lot of these things. We want to increase the profit margin. We want to be good stewards of the earth. We don't want to waste a lot of material. So find us the optimal cylinder whose dimensions will give us 12 fluid ounces that uses the least amount of material. Okay. So when you read this, that's what it says. The least amount of material, the least amount of aluminum. So that's why it says minimize the amount of aluminum. So what is it then? Let's draw a picture here. I'm not going to use the one they gave me. Let's draw a picture of a generic cylinder. A cylinder has two important features, right? A radius and a height, which is the distance between the top circle and bottom circle. Those are the two main dimensions. We want to find the optimal dimensions of a can that minimizes the amount of material used to construct the can. So assuming no waste, what is it then that we're trying to minimize? The material used translates to what quantity? Surface area, good. We're trying to minimize the surface area. Now, you should be able to generate the formula for the surface area of a cylinder if you don't have it memorized, okay? So the surface area of a cylinder, just think about if you had to paint it, right? There's a circular top and a circular bottom. I'm gonna call this A for area. The top and bottom are circles. What's the formula for the area of a circle? Yeah, pi r squared. And we have a top and a bottom. So there's two of them, okay? Plus the lateral surface area, we call it, which if you were to take this and cut it open with your parents' permission and help possibly, right? If you were to cut it up the side and lay it down flat, it would look like a what?
Rectangle.
A rectangle, good. And this is the height, which is the height of the cylinder, but the length of the cylinder ends up being the what of the top? The circumference, good. So this is the circumference, which is 2 pi r. And of course, how do we find the area of a rectangular rectangle? Length times width. So this is 2 pi r times h. All right. So we got the top and bottom, 2 pi r squared, plus the lateral surface area, 2 pi r h. So that is our primary equation. That's what we're trying to minimize. What's the constraint now? What's going to keep us from making this thing super, super tiny? Do you want to look at it and pass it around? The fact that it has to hold 12 fluid ounces. I already looked at it. Okay, awesome. So I'm going to come over here and say then that my constraint, which is 21, I'm just going to call it 21.6, okay, for simplicity in writing. Or let me just call it 22, okay? 22 cubic inches, and that's a measure of what? Cubic inches. Volume, V. So what is the formula for the volume of a cylinder? Of a cylinder. Yeah. So this is really a circular prism, whereas the length times width times height is a rectangular prism. All you have to do to find the volume of a geometric prism, which basically has a geometric shape on the top and the bottom, and then some distance between them, it's just the area of the face or the base, that's what we call it, and then times the distance between them. So that's why a rectangular prism, it's length times width, that's the area of the top, times the height, which is between them. So this is going to be the area of the top, which is pi r squared, times the distance between the top and bottom is h. A circular prism is a cylinder. This is the area of the face or the base times the distance between them. So I know then that pi r squared h is equal to 22. This is our constraint equation or the auxiliary equation. And over here is the primary. So now remember, we need to get our area, surface area equation, either in terms of r exclusively or h exclusively. Which one is easier to solve for in my volume equation, h or r? H, right? Is that also the easier one to plug into? Yeah, so in this problem, all roads lead to H. So I know that H is equal to 22 over pi r squared, all right? And again, I'm gonna box that because I might need to come back to that to find the height. But for now, I'm using it to plug into my first equation. So I get the surface area of a rectangular, or I'm sorry, of a rectangular cylinder, right circular cylinder, sorry, is going to be 2 pi r squared plus 2 pi r times 22 over pi r squared. All right, and then once I get that into a single variable, this is where we look for our relevant domain. What's the smallest then the radius can be? Or what's the lower bound, I should say? Are we going to have a negative radius? No. What can the radius be 0? No, but it could be anything greater than 0. So I know the radius has to be, yeah.
When we're doing these questions, do we have to do the bounds to get points, or is it just alphas?
No, the bounds are important, yeah, for points, yeah, and to help you. Now, in this case, the upper bound, we don't really know what it is, right? And again, it's not super important, but I do know that when the height gets smaller and smaller, the radius can get bigger and bigger. Yeah, hey. So we're talking about like some very, quite a variety in cans. You can get the cans that are like the Red Bull cans that have a small radius and a really tall height, right? And, you know, I don't like those tall, skinny cans because when you grab it, your fingers touch around the back end and it's kind of gross. Okay. But if that's the optimal can, then Red Bull is doing it right. And all the other soda cans out there are shaped wrong and they're producing cans that are not optimal size and it's costing them more money. Or you got the cans that can be really, really wide that are not very tall. And those, you know, those you have to have like 2 hands just to pick it up. It's probably going to be somewhere in between the 2 extreme cases. All right, so now we're going to take the derivative, set it equal to 0. But wait, there's first off, we could do what? Simplify when? Early and often. I know a pi can divide out here, and so will one of the r's. So let's do that. 2 pi r squared plus, I can multiply the 2 times 22. So I'm just going to call that 44, right? 44 over r. That's what it simplifies to. Or 2 pi r squared plus 44 r to the negative first. The top one gives me a nice formula for the area, surface area in terms of the radius that I can evaluate. The bottom one makes it kind of in a nice format ready for differentiation. So now let's do that. The derivative of a with respect to r, or a prime of r. It doesn't matter which one. Power rule, yeah? 4 pi r to the first minus 44 r to the negative second. Easy. Now, because we want to use it, we want to clean it up. And you could either factor out least powers, or you could factor out after you clean it up. Let's clean it up first without factoring out least powers, because again, I think more people would probably do it this way. But factoring out least powers, which would be r to the negative second and then a 4, cleans it up in the quickest, fastest way. But if you just take your denominator and put it in the bottom, now you can get a common denominator. So I need to multiply the first one by r squared over r squared. And I end up with 4 pi r cubed minus 44 all over r squared. Now, for the sake of this problem, let's go ahead and factor out the 4 from the top, and that makes it pi r squared minus 11 all over r squared. And I know that that can factor, but it's not a perfect difference to square. So I'll just leave it like that. R cubed, thank you. R cubed, where? In the top numerator. 4 in the bottom numerator. Wait. 4r cubed minus 44. I factored out a 4 pi r cubed in the top numerator. Thank you. Yeah, thank you. All right. So now we have a cleaned up version of the full-fledged factored version of the derivative. It's going to be undefined when r is 0. It's not in our domain, so we don't even worry about it. So now I could just set it equal to 0, and that's going to be when the numerator is 0. Make sure you're setting it equal to 0. So when you solve, that's going to be 4 pi r cubed minus 11 equals 0. Divide through by 4, you don't need it. You're going to get r cubed equals 11 over pi. And when you take the cube root of it, I'm going to say it's approximately the cube root of 11 over pi. Okay, we don't take plus or minus when I take the cube root. Now, again, that's the only critical value in our relevant domain. That's going to be the answer, especially since we know the two extreme cases are approaching zero volume, right? As the radius gets smaller and smaller and the can gets taller and taller, it's approaching zero. As the can on the right gets shorter and shorter and the height is zero, the volume zero. So somewhere in between there through a continuum, we have a maximum. So we can be confident this is correct. All right, and that's inches. Now, I'm not going to finish out the computations because again, after all, I'm using 22 as an approximate answer. But once I found the radius and I know it's my optimal value, now I answer the frickin' question, okay? And to do that, it asks you for what? The dimensions. So once I find the radius, I can plug it back in here to find the height. Or if it asks you for the surface area, you can plug it back in right here, or maybe that's not the most useful version, this one right here to find the area. So there you go. Now, when the calculations are done correctly with the decimals intact, it turns out that the optimal dimensions are going to be approximately a diameter of 3 inches and a height of 3 inches, believe it or not. You can verify at home, but the radius ends up being about 1.5 and the height ends up being around 3, okay? Which means that the optimal 12 fluid ounces soda can would be one that would fit perfectly inside of a 3 by 3 by 3 cube, right? Yes, approximately 3 inches by 3 inches. Okay, now, if you know something about the can itself, like the modern day can, it's not 3 by 3, right? Those 3 by 3s are closer to those little squatty ones that hold less, right? It turns out though that the width is pretty darn close to 3. If you're at lunch and you have a tape measure and a soda can, measure it. The today's width is almost ideal, but the can is not, right? The can is about 4.75. All right. So then the question is, well, why are most soda companies not at the optimal? Yeah.
Is it because our hands wouldn't fit around it very well?
Yeah, there's a lot of consideration, right? If the optimal width of the can had been like 5-6 inches, they probably still would have gone with closer to 3 inches because there's feng shui, there's ergonomics at stake, right? And they probably ran several tests where they're just like telling people, here, hold this and rate how that feels. Now hold this and rate how it feels, right? And the average human hand, you know, holding something that has a 3-inch diameter probably feels pleasing, right? And so once they decide that, hey, we're going to go with like 3 inches about, but what does that mean then? If we need more space, if we're not going to make it up widthwise, we got to make it up vertically. And so that's why the can is a little bit taller. Now there's also other things to consider, right? There's also air inside the cans to keep it pressurized.
I think the best part about this is that we just had a Celsius and Red Bull at the ready.
Sweet. Yeah, see these Red Bull, ooh, gross, right?
What?
Red Bull is deliberately going out of their way to spend more money on cans. Why? That's marketing, right? Engineers probably aren't the best people to sell it.
Wait, Courtney, you have huge hands. Wait,
Why is it approximately and not?
Well, because I approximated 22, right? The actual value is 21.6. Yeah. If you look at today's cans, like notice there's it's bell shaped on the bottom to help keep the can pressurized. There's air in here, so there's more volume than just 12 fluid ounces. But if you notice these little bevels around the top and bottom, they're not just to help these things stack. The thing at the top is actually a lip rest. If you really want to understand kind of how, and you don't even notice that, but drink out of a can that has this nice beveled lip rest at the top, and you're like, oh, that's pleasing when you compare it to like cut open a can of green beans when you get home and just drink right out of the cylinder. You're like, oh, this is disgusting. Oh, my lip and green bean juice, right? So anytime you cheat something volume wise to make an indentation for stacking or air, you're going to make it up vertically. Okay. But there you go. Happy soda can. All right. Now we beg the question, what came first, the soda can or the soda can machine? Maybe the machines were made first and these were the only size cans that would fit in them. So, right. Yeah. All right. So there you go. Happy National Aluminum Soda Can Day. Yeah. All right. I'm going to skip example 10 and possibly come back to it. Let's look at example 11 now. It says to find the volume of the largest cone that can be inscribed in a sphere of radius 5. Okay. All right. So how do we know this is optimization to start with? Largest. Okay. This is one also where a picture can help. Let's draw a sphere, but of course we're drawing a cross section of a sphere called a circle. And the radius is 5. So let me go ahead and establish that. I'm just going to draw this line right here. And we'll call that 5. Okay. We don't know if it's 5 inches, 5 miles, whatever, but there it is. Now I want to draw a representative cone that's inscribed. That means it's inside. So my cross section of a cone is going to be a triangle. Now, what's the optimal cone going to be? Is it going to be one that lives way up here? Or is it going to be one that lives way down here? Right? Those are non-typical cones. More than likely, it's going to be one that's somewhere in between there. Okay. In fact, you can see that as the height of the cone approaches 0, we're approaching the top one and it collapses on itself. As the height of the cone reaches 10, which is the diameter of the circle, the cone collapses on itself horizontal. So again, the extreme cases geometrically are 0. That's going to be the minimum. So when you're drawing this, draw again just a representative one. It's going to probably dip below the center of the circle. And then if you want to draw straight across, you can, but remember that it's going to have this like circular base. Okay. Now the optimal dimension here's what the largest cone, and since we're doing 3-dimension, this is volume. Here's the volume of a cone. The volume of a cone is pi thirds r squared h. It's basically the volume of a cylinder. Take a cylinder, carve out 2/3 of it that doesn't resemble a cone, and you're left with the volume of a cone. So keep that memorized. Now let's go ahead and label the dimensions. The dimension right here is little r. Now that's the radius of the cone, not the radius of the sphere. Of course, the height, you could call the entire thing from top to bottom. You can call that whole thing h. But here's what I've come to discover. All right. If you label large parts, you're going to have to come back and use subtraction or fractions to measure smaller parts. So here's what I would recommend. Get in the habit of label your small parts. And then if you had to, you can build up, Jackson, smart parts. Small parts. And then when you build up, you can use addition or multiplication. So here's what I'm going to do. I'm going to let this piece here just be y. I don't want to call that h for height because it's not going to be the height. All right. And of course, this dimension here I know is 5. So essentially, if you want, we're letting h equal y plus 5. And I'm not even going to use h in my equation because it's going to be confusing. Okay. So for me, I'm trying to maximize the volume. And I'm going to write my equation. The volume then is pi thirds. That's good. I'm okay with r, so I'll use r squared. But the height, I'm going to call it y plus 5 instead of h. All right. If you call the whole thing h, that's fine. but then y is going to end up being h minus 5, and we don't want subtraction. And I'll show you why here in a second. So that's the equation that I'm trying to maximize. You pull the formula off the formula chart, but you custom tailor it to fit your needs, okay? So there you go. If you want to make this note up here, that's fine. You don't even have to say h equals y plus 5. So I have the volume now in terms of r and y, where y is the distance above or below the center I need to go in addition to 5, okay? What's the constraint? Well, the constraint is the sphere itself that has a radius of 5. So I need to somehow relate my radius, little r, to y to 5 in my sphere. So that's going to be your constraint equation or your auxiliary equation. How can I relate little r to little y to 5 in this problem? Geometric tomfoolery is the answer. Here's what I would here's another reason why I labeled the small part. If you draw a line from the center here to here, that's 5, isn't it? It's another radius. But look what that highlights now. That highlights a right triangle. And does that give us the ability to relate r to y to 5? Yeah, by the Pythagorean theorem. So r squared plus y squared equals 5 squared. Yeah, now there is a variation on this problem where you're fitting a cylinder in instead of a cone. And the only difference for the cylinder is the height of the cylinder is not y plus 5, it's y plus y or 2y. But you would still relate them using the Pythagorean theorem, okay? Now come over here. Do you want to solve it for y or for r squared? Yeah, I don't even think I'm going to solve it for r because I have an r squared over here. Or if you did solve it for r, you can plug it right back in and it squares. So let's do that. We know that r squared then is 25 minus y squared. And if I needed to solve for r, what the heck? It's the square root of that. No big deal. So when you plug it in for r and square it, the radical goes away. Or if you realize you don't even need to do that, you're going to get pi thirds times r squared, which is 25 minus y squared times y plus 5. And now let's think about the values that y can take on. We should be able to get a lower bound and an upper bound. Remember, y is the directed distance, we say, above or below the center. So what's the smallest y could be? If I retreat back up towards the top, y is going to be a negative number, right? So like in that original example where it was tall and wide, y was approaching -5. But it can't equal -5 because then it would collapse, right? What would be the max I can go below the center? 5. And again, if it equals 5, then I've collapsed it down horizontally. So there's your interval for y. So now having a negative critical value would make sense. For instance, if y ended up being -1, then I would come back up here and retreat, and then my ideal cylinder would look like that. Okay, so that's why it's important to realize y is a directed distance. All right, so now that I have my equation in terms of a single variable, I have my relevant domain, I'm going to take the derivative. And I don't think I'm going to bother expanding out here. I think I'm just going to do the product rule. Okay, so here's my product rule. V prime equals pi thirds is going to go along for the ride. So beefy brown bracket. I'm not even going to make it part of the first factor. The derivative of the first factor with respect to y is -2y times the second one goes along for the ride, plus 25 minus y squared goes along for the ride, times the derivative of y plus 5 is 1. And I guess I should close the beefy bracket with the right color. Beefy brown. Okay. Now let's simplify that. Working straight down, we get pi thirds and then beefy bracket. Now I'll distribute so I can collect like terms. I'm going to get -2y squared minus 10y, and then plus 25 minus y squared. That's looking good. Combined like terms, right? Starting with the highest degree. So that's going to be minus 3y squared minus 10y plus 25. All right, is that thing ever undefined? No, it's not. So I need to set it equal to 0, which means I'm going to need to try to factor it. If I'm going to try and factor it, I'm going to pull out I can't pull out a 3, right? Unless I make it a fraction. But I am going to pull out a negative just because it's a lot easier to factor with a positive leading coefficient. 3y squared plus 10y minus 25. And now we set it equal to 0. Again, there it is. From here, it's academic at this point, right? There could be up to 2 solutions. If we can't factor it, we have the quadratic formula we can use, and we can go from there. Now, does anyone know how to factor this? Does it in fact factor? Have I been doing it right so far? Does anyone catch a careless mistake? I know 3 is prime, so if it's going to factor, it's going to be a 3y and a 1y. And then 25 is not prime, but it's either a 25 and a 1, which is going to kind of make the sum and difference combinations too big. So maybe it's 5 and 5. Will that work? Positive 15 on the outside, negative 5 on the inside. Does that work? Negative 25, and then that gives me a 15 minus 5 is 10. Yeah, it does work. Well, I'll be dang, right? Yeah, and for these non-calculator ones, it's either like guess and check, where guess and check works, or it will factor. So over here on new column, so we know the critical values are going to be y equals negative 5, that's from the second factor, or y equals 5/3. Dang it, what do we do if we have 2 critical values and we're trying to find the absolute maximum? Yeah, we can check to see if one's in our relevant domain. And of course, negative 5 is not. But we've already considered negative 5. That's the extreme case. So if you did have more than one, since you are looking for the absolute, you could actually just plug both of them into your actual volume equation right here and take the one that's the larger of the 2 numbers, right? But in this case, negative 5 collapses to 0. So there is our optimal value right there. And now from there, we answer the friggin' question, right? Find the volume of the largest cone. All right. So in this case, we didn't want the dimensions. We wanted the volume. So the largest volume is, and I'm just going to plug it back into the highlighted volume, pi thirds times 25 minus 5/3 squared is 25 ninths times 5/3 plus 5. And if there were units, are there any units? No. But if there were, I would put, feet squared, cubic feet, so units cubed. There you go. Nifty little problem. The Pythagorean theorem. The reason we do this type of problem is because Mr. Wenzel likes them. In fact, in the worksheet, you'll see that he has a big problem. He's trying to do something like this, and he doesn't really know how to do it so well. Just like I don't know how to spell the capital of Botswana. What's it called? Mogadishu. I don't know. Yeah. All right. So we didn't quite finish Ouagadougou. There you go. We will finish tomorrow, and we will move on to the next section tomorrow. Okay. And we'll probably quiz on Wednesday. All right. But tomorrow we're moving on to related rates because all we have left to do really is example 12. And we'll come back and just set up example 10. Optimization. Yeah, just optimization. Is that C lunch already? Yeah, wow, time flies when you're doing math. Boy does it. No, probably not this week. Yeah, I want to make sure we finish optimization related rates. So test next week. Wednesday. Yeah. All right.